welcome to this problem walkthrough. In this session, we'll tackle problem number 2025, split array into two arrays to minimize some difference. We'll explore the problem statement, dive into various approaches, and analyze their complexities. Let's get started. In this problem, you're given an integer array called nums, which always has an even length of 2 times n. Your goal is to split this array into two separate arrays, nums1 and nums2, each containing exactly n elements. The challenge here is to minimize the absolute difference between the sums of these two arrays. This absolute difference is calculated as the absolute value of the sum of nums1 minus the sum of nums2. Essentially, you're trying to make the sums of the two arrays as close to each other as possible. The output of the problem is a single integer, which represents the smallest absolute difference you can achieve by splitting the array optimally. The input array, nums, can have a length between 2 and 30, and the values within the array can range from -1 million to +1 million. To make this more concrete, let's look at an example. Suppose nums is given as 1, 2, 3, 4, 5, 6. One way to split this array is to assign nums1 as 1, 2, 6, and nums2 as 3, 4, 5. The sum of nums1 becomes 1 plus 2 plus 6, which equals 9, while the sum of nums2 is 3 plus 4 plus 5, which equals 12. The absolute difference between these two sums is abs, 9 to 12, which equals 3. In this case, no other way of splitting the array results in a smaller absolute difference, so the output is 3. This demonstrates how the goal is to find the split that minimizes this absolute difference. Now consider another example where nums is 10, 20, 15, 25, 30, 35. Here, one optimal split is nums1 as 10, 25, 35, and nums2 as 20, 15, 30. The sum of nums1 is 10 plus 25 plus 35, which equals 70, while the sum of nums2 is 20 plus 15 plus 30, which equals 65. The absolute difference in this case is abs, 70 to 65, which equals 5. This is the smallest difference achievable with any valid split. Additionally, there are important constraints to consider. The length of nums is always even, ranging from 2 to 30, and each element of nums falls between -1 million and +1 million. Each number must belong to only one of the two arrays, and the goal is to output the minimum absolute difference. For edge cases, small inputs like arrays of length 2 will have straightforward calculations, while arrays with negative numbers, large values, or identical elements will test the robustness of the solution. For instance, if all elements are equal, the absolute difference will always be 0 since the sums of both arrays will match exactly. To solve the problem of splitting the array into two subsets with minimal sum difference, we can start by considering a brute force approach. The intuition here is straightforward. Given an array of size 2n, we need to select n elements to form the first subset, nums1, while the remaining elements automatically form the second subset, nums2. By generating all possible combinations of n elements from the array, we can calculate the sums of nums1 and nums2 for each split, compute their absolute difference, and track the minimum difference. However, the primary downside of this approach lies in its computational complexity. Generating all combinations of n elements from a 2n-sized array involves O(2n n), which grows exponentially as n increases. For example, when n exceeds 10, the number of combinations becomes infeasibly large, making this approach impractical for larger inputs. While simple in concept, the brute force method is not efficient for solving the problem within reasonable time constraints. An optimized solution to overcome the limitations of brute force is the meet-in-the-middle approach. The key idea here is to divide the problem into smaller, more manageable subproblems. Instead of generating all combinations at once, we split the array into two halves and calculate all possible subset sums for each half independently. This drastically reduces the size of the problem from 2n elements to n elements per half. Once we have the subset sums for both halves, we can combine them intelligently to find the closest sums between the two halves. By sorting the sums from one half and using binary search to efficiently find the closest complementing sum in the other half, we can determine the minimum absolute difference. This approach leverages the reduced problem size and efficient search techniques to achieve a significant improvement in computational complexity. Specifically, generating subset sums for each half takes O(2 to the power of n), and the combination step involving sorting in binary search reduces the overall complexity to 2 to the power of n*n, making it much more feasible for larger input sizes. Given the trade-offs between the two approaches, we chose the meet-in-the-middle strategy for its balance of efficiency and feasibility. While the brute force approach is simpler to implement, its 2*2n time complexity makes it impractical for larger inputs. On the other hand, the MITM approach reduces the problem's computational overhead by dividing the array into two smaller halves and leveraging pre-computed subset sums and efficient search techniques. This method guarantees correctness and achieves a significantly better time complexity of 2 to the power of n*n, making it suitable for constraints where n is up to 15, or an array size of up to 30 elements. The key insight, or aha moment, behind this approach was realizing that the problem size could be reduced by splitting the array in half and pre-computing subset sums, which dramatically improves efficiency while maintaining accuracy. However, it's worth noting that even the MITM approach becomes computationally expensive for very large values of n, such as n greater than 20, due to the exponential growth of subset sums. In such cases, further optimizations or approximations would be necessary to scale the solution. In this problem, we are tasked with dividing an array of size 2*n into two subsets of size n each, with the goal of minimizing the absolute difference between their sums. To achieve this, we must carefully split the elements into two groups, nums1 and nums2, such that the absolute difference, calculated as abs, sum, nums1, sum, nums2, is as small as possible. We start by considering a brute force approach. This involves generating all possible combinations of n elements from the array to represent nums1, while the remaining elements form nums2. For each split, we calculate the absolute difference between the sums of the two subsets and keep track of the minimum difference found across all combinations. Although this method guarantees the correct solution, it's computationally expensive, and we'll explore why in subsequent steps. To break down the brute force approach further, the first step is input validation. We must ensure the array length is even, as it should be 2*n for the problem to be well defined. Next, we generate all possible combinations of n elements from the array. This can be achieved using recursive backtracking or efficient library functions like Python's itertools.combinations. For an array of size 2*n, the total number of combinations is given by the binomial coefficient c, 2n, n. Once the combinations are generated, we calculate the sum of elements in nums1 for each combination and derive the sum of the complementary elements in nums2. With these sums, we compute the absolute difference and maintain a variable, min_diff, initialized to infinity. This variable is updated whenever a smaller difference is encountered. Finally, after evaluating all combinations, we return the smallest absolute difference as the result. Now, let's analyze the complexity of the brute force approach. Generating all combinations of n elements from an array of size 2*n involves 2n, n operations, which grow exponentially with n. Additionally, for each combination, calculating the sums of nums1 and nums2 takes n time. As a result, the total time complexity is 2n, n*n, which becomes computationally prohibitive for larger values of n. Moving on to edge cases, it's important to consider scenarios like arrays with duplicate values, ensuring that combinations are handled correctly. For the smallest possible input size, such as n equals 1, the algorithm must still provide valid results. Key insights from this analysis include recognizing the exponential growth of combinations, leveraging symmetry in the problem to avoid redundant calculations, and identifying potential optimization opportunities, such as dynamic programming or greedy techniques, to reduce the computational burden. To implement this approach effectively, certain data structures are critical. First, we need a combination generator, which can be built using a recursive algorithm or a library function like itertools.combinations. Next, we require a variable, min_diff, to track the smallest absolute difference observed during the computation. For the subset sums, simple integer variables suffice to dynamically compute and compare the sums of nums1 and nums2. Let's illustrate this with an example. Suppose the input array is 1, 2, 3, 4, with n equals 2. The possible combinations of two elements are 1, 2, 1, 3, 1, 4, 2, 3, 2, 4, 3, 4. For each combination, nums1 is the selected pair, and nums2 consists of the remaining elements. We compute the absolute difference for each split and track the minimum. In this case, the result is 0, as the subsets 1, 4, and 2, 3 have equal sums. This walkthrough demonstrates how the brute force method works but also highlights its inefficiencies, prompting the need for optimization in more complex cases. To address the problem of minimizing the sum difference when splitting an array into two parts, we start by dividing the array into two halves. Here, nums1 represents the first half and nums2 represents the second half of the input array. The total sum of all elements is calculated to assist in determining the difference later. Next, we generate all possible combination sums for subsets of each half. To achieve this, we use the combinations function from the itertools library. For each possible subset size, ranging from 0 to the size of the half, we calculate and store the sums in the left_sums and right_sums dictionaries. Each dictionary key represents the subset size, and the corresponding value is a set of all possible sums for that size. These sets of subset sums will allow us to efficiently compute the minimum difference. At this stage, we also initialize the min_diff variable to infinity, which will be updated as we iterate through possible partitions. Finally, for each partition size k, we sort the subset sums for that size from the left half and for the complementary size from the right half. This sets the stage for using a two-pointer approach to find the closest pair of sums. Now, using the two-pointer technique, we aim to find the closest pair of sums between the sorted lists of subset sums from the left and right halves. We initialize two pointers, I starting at the beginning of the left list and j starting at the end of the right list. These pointers allow us to systematically explore pairs of sums. For each pair, we calculate their combined sum, cur_sum, and determine the absolute difference between twice this sum and the total sum of the array. This difference represents how far we are from an equal split, and we update min_diff if we find a smaller difference. To adjust the pointers, we check whether cur_sum is smaller or larger than half of the total sum. If it's smaller, we move the I pointer to the right to increase the sum, otherwise, we move the j pointer to the left to decrease the sum. This process continues until all relevant pairs have been evaluated. Finally, we return min_diff, which holds the smallest possible difference between the sums of the two partitions. Here, we start by dividing the input array nums into two halves, nums1 and nums2. This is done because the problem involves splitting the array into two subsets, and working with smaller halves simplifies our calculations. We calculate the total sum of the array, which will help us assess the difference between the two subsets later. Next, we declare two maps, left sums and right sums. These will store all possible subset sums for each half of the array, grouped by the number of elements in the subset. For example, leftsums.get2 will contain all sums obtainable by selecting two elements from nums1. We initialize these maps with empty sets for each possible subset size, from 0 to n. Finally, for each subset size, we call generateCombinationSums to populate these sets with all possible sums for both halves of the array. This ensures that we have pre-computed all potential subset sums before moving on to minimize the difference. Once we have all possible subset sums for both halves, we can start minimizing the difference. For each subset size k, we retrieve the sums for k elements from nums1 and nk elements from nums2, storing them in left and right lists respectively. To facilitate efficient comparison later, we sort both lists. The goal now is to pair sums from left and right and calculate the total sum of the two subsets they represent. We utilize a two-pointer approach for this. Starting with one pointer at the beginning of the left list and the other at the end of the right list, we calculate the current sum of the pair and determine the absolute difference between double this sum and the total sum of the array. If the current sum is less than half the total sum, we move the left pointer forward to increase it. Otherwise, we move the right pointer backward to decrease it. This strategy ensures we explore all possible pairings efficiently, updating min_diff whenever we find a smaller difference. The helper method generateCombinationSums helper is a recursive function that generates all possible subset sums for a given array. It takes the current index, the number of remaining elements to select, the current running sum, and the set that will store the results. If no elements are left to select, the current sum is added to the set, and the function returns. If the index exceeds the array bounds, the recursion also terminates. Otherwise, the function explores two paths, including the current element in the sum or skipping it. By recursively exploring all combinations, this method ensures that every possible subset sum is calculated and stored in the set. This pre-computation is crucial for efficiently solving the main problem, as it allows us to focus on minimizing the difference between the two subsets using these pre-computed sums. To solve this problem, we start by splitting the input array into two halves. For example, given nums as 1, 2, 3, 4, 5, 6, we divide it into nums 1 as 1, 2, 3, and nums 2 as 4, 5, 6. The total sum of the array is calculated as 21. Next, we generate all possible subset sums for each half. For nums 1, we compute subsets based on their sizes. Subsets of size 0 give 0, size 1 gives 1, 2, 3, size 2 gives 3, 4, 5, and size 3 gives 6. We store these results in a map called left_sums, where the keys represent the subset sizes. Similarly, for nums 2, subsets of size 0 give 0, size 1 gives 4, 5, 6, size 2 gives 9, 10, 11, and size 3 gives 15. These are stored in right_sums. This step sets the foundation for efficiently comparing subset sums from both halves in the next part of the solution. Now, we aim to minimize the absolute difference between the sums of the two resulting arrays. We start by initializing min_diff to infinity and iterate over subset sizes k, which range from 0 to n. For k equal to 0, we consider subsets of size 0 from both nums 1 and nums 2. Left_sums gives 0, and right_sums gives 15. Adding these, we calculate the difference as the absolute value of 21 minus 2 times 15, which is 9. This updates min_diff to 9. Next, for k equal to 1, we evaluate subsets of size 1. Left_sums has 1, 2, 3, and right_sums has 9, 10, 11. Here, the closest pair to the target sum of 10.5 is 3 from the left and 9 from the right, resulting in a sum difference of 3, which updates min_diff to 3. For higher values of k, no smaller difference is found. Ultimately, the minimum difference achievable for this example is 3. In another example, let's consider nums as 1, 1, 1, 1, 1, 1. Splitting the array gives nums 1 as 1, 1, 1, and nums 2 as 1, 1, 1, with a total sum of 6. We then compute subset sums for each half. For nums 1, subsets of size 0 yield 0, size 1 gives 1, size 2 gives 2, and size 3 gives 3. Similarly, nums 2 results in the same subset sums. Moving to the minimization step, we initialize min_diff to infinity. For k equal to 0, left_sums gives 0, and right_sums gives 3. Adding these, the difference is the absolute value of 6 minus 2 times 3, which is 0. Since this is the smallest possible difference, min_diff is updated to 0, and no further comparisons are needed. Thus, the minimum difference for this example is 0. Finally, consider nums as 10, 20, 30, 40, 50, 60. Splitting the array gives nums 1 as 10, 20, 30, and nums 2 as 40, 50, 60, with a total sum of 210. We calculate combination sums for both halves. For nums 1, subsets of size 0 yield 0, size 1 gives 10, 20, 30, size 2 gives 30, 40, 50, and size 3 gives 60. Similarly, nums 2 results in 0, 40, 50, 60, 90, 100, 110, and 150. To minimize the difference, we initialize min_diff to infinity and compare subset sums for k ranging from 0 to n. When k equals 1, the closest pair of sums minimizes the difference to 30. No smaller difference is found for other values of k. Therefore, the minimum difference for this example is 30. To analyze the time complexity of our solution, we first look at the step of generating combination sums. For each subset size I, we generate all possible combinations of size I for both halves of the array nums 1 and nums 2. The number of combinations of size I is determined by the binomial coefficient c, n, I, which, when summed across all possible subset sizes, results in 2n. Since we perform this operation for both nums 1 and nums 2, the total time complexity for this step is 2 to the power of n. Next, we sort the combination sums for each subset size. Sorting each subset of sums, which involves 2 to the power of n log 2 to the power of n operations, is repeated for all subset sizes. Since there are 2 n subsets in total, this sorting step also contributes 2 to the power of n log 2 to the power of n to the overall complexity. Together, these two steps dominate the time complexity so far. Now, let's look at the two-pointer approach used to minimize the sum difference. For each partition size k, we use 2 pointers to traverse the sorted lists of sums from left_sums k and right_sums nk. In the worst case, each iteration involves 2 to the power of n comparisons, as both lists contain up to 2 n elements. Since this process is repeated for all possible values of k, the total contribution of the two-pointer approach is n*2 to the power of n. Combining all the steps, we see that the time complexity of the solution is ultimately dominated by the combination generation and sorting steps, leading to a final time complexity of 2 to the power of n log 2 to the power of n. Shifting to space complexity, the primary factor is the storage of combination sums. Both nums1 and nums2 generate 2 n subsets, and storing their sums requires 2 to the power of n space for each half, leading to a total space complexity of 2 to the power of n. In addition to storing the combination sums, we can consider other contributors to space complexity. Sorting the combination sums uses extra space during the sorting process, but this is negligible compared to the space required to store the sums themselves. Beyond that, the algorithm uses a constant amount of auxiliary space for variables like min_diff, I, j, and cur_sum. This auxiliary space contributes only 1 to the overall space complexity. When we combine all these factors, the overall space complexity remains 2 to the power of n. This efficient use of space ensures that the algorithm is feasible for moderately large input sizes. To appreciate the efficiency of the optimized approach, let's compare it to a brute force method. The naive brute force approach involves generating all possible partitions of the array nums into 2 subsets, calculating their sums, and finding the minimum absolute difference. However, since there are 2n possible partitions for an array of size 2n, the time complexity of this brute force approach is 2n, which is computationally prohibitive for even moderately sized inputs. In contrast, the optimized solution focuses on subsets of nums1 and nums2 separately, reducing the problem's scope to subsets of size n. This drastically reduces the time complexity to 2 to the power of n log 2 to the power of n, making the algorithm far more efficient and practical for real-world use cases. Finally, let's evaluate the best, average, and worst-case scenarios for this algorithm. Regardless of the input, the algorithm always generates all subsets, sorts them, and applies the two-pointer approach. This consistency means that the best case, average case, and worst case time complexities all remain 2 to the power of n log 2 to the power of n. To understand why, note that generating all subsets of size I involves a combinatorial process proportional to 2 n, and sorting and comparing these subsets adds a logarithmic factor. The space complexity is similarly consistent, as it depends solely on the storage of 2 n subsets, leading to a space complexity of 2 to the power of n. In conclusion, this optimized approach achieves a significant reduction in computational complexity compared to the brute force method, transforming an intractable problem into one that is solvable for practical input sizes. When solving this problem, there are several common mistakes to avoid. First, incorrect subset partitioning is a frequent issue. Remember that the problem requires splitting the array into 2 subsets of exactly equal size. If you generate subsets with uneven sizes, the output will be invalid because the calculations depend on this balance. It's also important to account for edge cases, such as arrays with duplicate elements or the smallest possible input size. For example, if the input is 1, 1, your solution must treat the subsets 1 and 1 as valid, without ignoring duplicates. Another pitfall is using inefficient implementations. Brute force solutions that don't prune the search space can lead to exponential runtime, which is especially problematic for larger inputs where n can go up to 10,000. This inefficiency often results in time limit exceeded errors, so optimizing your approach is critical. Another issue to watch for is floating point precision errors. When dealing with sums or averages, relying on floating point arithmetic can introduce subtle bugs. For instance, directly comparing two floating point values for equality may fail due to precision limitations. Instead, compare their difference against a small tolerance value to ensure accuracy. Misinterpreting problem constraints is another common oversight. For example, the constraint that the array size will always be 2*n simplifies the problem significantly. If you misunderstand or ignore this, you might add unnecessary complexity to your solution, such as by introducing redundant checks or extra layers of logic. Leveraging the constraints effectively can streamline your implementation and make it more efficient. To perform well in interviews, it's essential to recognize key patterns in this problem. For example, it shares similarities with the subset sum and partition problems, which often involve combinatorics, dynamic programming, or greedy strategies. Being able to identify these patterns early can guide you toward an optimal approach. Time complexity trade-offs are another critical discussion point. While brute force might work for small inputs, you'll need to optimize for larger constraints. Interviewers may assess your ability to transition from a naive approach to something more efficient. Space optimization is also worth emphasizing, as many solutions, especially dynamic programming, can be memory intensive. Demonstrating ways to reduce space usage can set you apart. Finally, always articulate how you've handled edge cases, such as duplicate numbers, zeros, or very large values. This shows a thorough understanding of the problem and attention to detail. This problem is closely related to several other LeetCode challenges, which can help you build a deeper understanding of the underlying concepts. For instance, partition equals subset sum requires dividing an array into two subsets with equal sums, which is a foundational problem for subset partitioning. Target sum focuses on finding subsets that achieve a specific target sum and often involves dynamic programming or backtracking, making it a good practice problem for this challenge. Another closely related problem is minimum subset sum difference, where the goal is to minimize the difference between the sums of two subsets. Finally, k equals sum subsets extends the idea to partitioning an array into k subsets with equal sums. This variation tests your grasp of combinatorics and recursion, further reinforcing the skills needed for this type of problem. There are multiple approaches to solving this problem, each with its own trade-offs. Dynamic programming, for example, is a powerful method that uses a DP table to track achievable subset sums. While this can significantly reduce the search space compared to brute force, it comes with a trade-off. The space complexity, which can be as high as O(n*) target sum, may become impractical for very large target sums. Backtracking with pruning is another effective approach. By generating subsets recursively and pruning branches that violate constraints, you can improve efficiency compared to pure brute force. However, this method still has exponential complexity in the worst case. Finally, greedy algorithms, while less common for this problem, can provide quick approximations for certain variations. The trade-off here is that greedy methods may fail in edge cases and don't guarantee optimal solutions. Understanding these approaches and their limitations will help you choose the most appropriate one based on the problem's constraints. Great job following along. To conclude, we summarized the key ideas and techniques, highlighted the main takeaways, and discussed when to use the approaches we've covered. Thanks for watching, and happy coding! That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!